Hello guys, what's up? I'm Mohammad Fouad, back with another video about programming. Welcome to the second part of our machine learning course that I have recently launched. If you're new here, my name is Fouad. I make videos about programming, Python, and more specifically, machine learning. Now, if you are interested in any of these, the only thing that you've got to do is to go ahead and hit the subscribe button, and you can also hit the bell so you get notified when I post a new video. So anyways, what are we gonna be learning today? Well, today we're going to be learning about cost function. Now, cost function plays a really important role in both machine learning and neural networks. We will use it from now all the way to the end of the course, and we will need it in many different areas, especially in neural networks. So today I'll explain what is cost function, the formula for it, and we'll kind of start building that up to linear regression, which is part of regression in supervised learning, which is part of machine learning. Now, if you don't know what supervised learning, regression, and these stuff are, I've explained them in the previous episode in the part 1 for this course, and here is the link up here. You can watch it, learn those, and come back here. So without further hesitation, let's dive right into it. Alright guys, so as I said, today I will explain a little bit more about linear regression, but the main objective of this video is to learn the cost function. And as I said, cost function is really important, and we will use it from now on all the way to the end of the course. We will use it in linear regression, in logistic regression, and in classification problems, in neural networks. We'll use it everywhere, so it's really important. So in the next videos that I'm gonna post for this course, I will explain linear regression completely and all the algorithms needed for it, like gradient descent, and we will learn how to do it completely. But now I'm just saying a little bit of it for you so you can understand the cost function a little bit better, so we can use the cost function with a little bit of couple of examples here and there, so you better get the intuition of it and you get the actual meaning of it. Alright guys, as I said, in linear regression we have a bunch of inputs and a bunch of outputs. So these are our inputs and these are our outputs, and we mostly have a bunch of inputs and a bunch of outputs. So I'll draw them here for you as a representation, and we have one output for every single input. As you can see, one input here, one output here, this input, this output, and these can vary based on what we are talking about. Now, the main objective of machine learning is to get us from our inputs to our outputs. You might ask, why would we do such thing? Because we already have the answers for certain inputs. Well, the problem is that we don't always have all the outputs for every single input possible. That's basically impossible to have it. It will take like more than 1,000 lines of code to explain every single thing to a computer. I will explain it in this video right here. So what we try to do is make the computer learn how to get certain outputs based on the input they have. And we use these examples that we already know the answer for them to teach the machine learning model. So the machine learning model will try to get these outputs from these inputs, and it will try to guess and learn how to do it. So the thing that is important for us is how to do it, so that next time that we have an input which we don't know the answer for it yet, we will know how to get the output or the answer based on the trainings that we've done previously. So now we will use this way to get the output for this special input. So that's the general idea about linear regression. Now, to make you understand it better, I'll try to give an example. Alright, let's say we have this chart over here, and the problem that we have is to calculate or have an estimate for the house value based on how big the surface area of the house is. So what I mean by that is, let's say we have a house that is 100 meters squared, and the value for that is $200 or pounds. I'm just gonna say pounds, right? So as you can see, the point that we will have would be here. Let's say we have another house with the surface area of 200 meters squared and the value of, you guessed it, 400. So as you can see, this point that we said will correspond to here. Now we will have a bunch of more examples here and there spread it out in our graph. So if you want to use machine learning for this problem, what we try to achieve is to have a machine learning model that will estimate the value of the house based on any points given in this scale over here. So as you can see, for this point in the scale, we don't have any value yet, but the machine learning model will use this data that we already have to get an estimate for what the value of this house with this area is gonna be. And you probably guess it's gonna be about somewhere here, which let's say is equal to 700 pounds. So as you can see, that's the machine learning model purpose. So there's two ways that we can do it. We can either use magic or mathematics. Well, I don't know how to use magic, then you can go ahead and learn that by yourself, but I know how to use mathematics for this. And the way that we use mathematics is by finding a perfect or a really good function. Now, in this example, we are talking about linear regression, which will try to get a linear function for the data set that we have. Now, you might heard me say data set. What is a data set and what is training data? So that's a really good question, and I'm gonna explain that to you. In every single machine learning question or problem that we will have a training set. And every training set contains two things, two variables. First, the x variable, and second, the y variable. You remember this example that I told you about, the inputs and the outputs. Well, that's basically what it's saying. The x is the input and the y is the output. So what we are trying to say is, for this special input, we want this output. And we will have a bunch of these as well. They're not gonna be similar. I'm just gonna index them with I. And we will have a lot of these examples. As you can see, for this model that we have 1, 2, 3, 4, 5, 6, 7, 8 training examples. We have 8 of these parentheses that tell us for what input, what output we have. And the machine learning model uses these to learn a way, or in mathematics, to learn a function that fits this data really good. So next time that we have an input that doesn't exist in our training set, we will find the value for it because we have a function that we can just plug this in and get the answer for it. So as I said, this is what a training set looks like, and the number of training set is shown by m. So whenever you see m, it means how many training examples we have. So as you can see here, we have I training examples. Sometimes we have 2. In this example, we have 8 training examples. So for this special question or problem that we have, m is equal to 8. So that's what basically a training set or training examples. And before we get any further, let me tell you something. This problem that we have is really simple. It's basically one of the most simplest problems that you can have for linear regression. Usually we have many different features or variables or inputs as well. Let's say we have another variable or another set of axes which represent the number of rooms, and we have a bunch of values for that as well, and the price of the house will be different depending on the number of the rooms as well. So the training set will now look like something like, and you might heard me, we call these features as well. So the inputs, we call them features as well. So as you can see, it will get more complicated as we add more features. But it doesn't matter because we have the machine learning model here. And that will help us solve these really complicated stuff. If we want to try to solve this with our own minds, we won't be able to do it. Because let's say we add another feature. Let's say we add what floor the flat is on, or which zone of the city it is on, or which city it is in. So based on that, the function that we need to find for it will be different. And as you can see, it will become like a 4D or 5-dimensional graph. And it's literally impossible to even draw it so we can understand it. That's why we use machine learning to find the best possible function for our data. Now, what is a cost function? We said all of this to find out what a cost function is. Well, in simple words, cost function allows us to see how accurate we are with this function that we guess here. So again, to remind you, this line that I've written here is gonna be a mathematical function. It's gonna be a linear function, which will look like something like this, and it can go as long as we want. And this line, this mathematical function, is basically this flash that are drawn here. It's basically the way of getting outputs based on input. Cost function allows us to see how accurate we are with this function with this mathematical function that we have. By the way, the other name for this mathematical function is a hypothesis, and this is how we write it. And we use the letter h and the parentheses to show this mathematical function. So this can be equal to theta 0 times x0 plus theta 1 times x1. And these x's that we are written here are the features that we have. We might have one of them, we might have two of them, and so on. So the cost function, as I said, will tell us how far away we are from the actual answers that we are supposed to get. So basically this hypothesis function starts from something random. We use some random values for these theta values to get an output here. For these examples that we have here, the theta value, we don't need this theta 0 here because we only have one feature if we ignore this value here. So for this example that we have, we can see that the theta value is equal to 2. So theta is equal to 2. Why? Because if we use the training set that we have, we will see for any input, the value of the output is basically twice as much. So for input 100, the output is 200. For input 200, the output is 400. So that's basically this. And if I want to write it mathematically, we will say the hypothesis x is equal to 2x, which means y is equal to this. And we want to get the best hypothesis so that we get the nearest answer to the output that we were supposed to get. So we try to find the really good hypothesis here to get this output for this input here. And as you can see, if we choose number 2 for our value theta, we will have the perfect answer. Why? Because if we try it here, we can see we will get the exact output for that exact input. And the cost function here will tell us how far away we are from our answers. And if you haven't already guessed, the cost function will return the value 0 because we are on point with the values we've chosen for our hypothesis function. So what does the formula for the cost function look like? So this is what the formula for the cost function looks like. We say j of theta, so this j of theta is the cost function, is equal to 1 over 2m. I don't think I've mentioned this before, but the general form of the cost function looks like this, and we tweak it a little bit for every single situation. For example, for logistic regression, we tweak it a little bit to get a correct mathematical function. For neural networks, we tweak it a little bit to get the correct one as well. But this thing that you're seeing here is basically the general formula for the cost function. So this basically means sum, and it means it's like a for loop in computer science. We start from I equal to 0 and we go to m, and as I said, m is the number of training examples that we have. This hypothesis theta of x is our prediction for this input, and we want to see how far away from the actual answer for this input that we had. So you see this example, this training set that I wrote here. We use the hypothesis function to get this output from this input. And as I said, it will not be right the first time. We have to do a couple of tests here and there to get the right answer for it. And what we always try to do with the cost function is to try and minimize the value of it. So we always try to make this equal to 0. It doesn't matter if it doesn't go exactly to 0, but we want it to go as close as possible to 0. And you have probably noticed this to the power of 2 over here, and that might remind you of the squared error function in statics. And this is basically the same thing. It's the squared error function. So this is the other name of it. So that's how it works, and let's use this function over here and calculate something for our other problem that we have. So let's say we only have this training example, and this training example says that for input 100, we have to get the output 200, right? That's what this is saying. Now first, we start with some random values for our theta value. So the hypothesis function at first will look like something like this, okay? And if we use it, you'll see the value is not going to be equal to 200. If we use 100 for our x, the value that this hypothesis function will output is going to be 100, but it is supposed to output 200 for us. So we calculate how far away from the answer using this cost function. If we try to use it, you'll see that it is going to be equal to 1 over, we only have one training example here, so 1 over 2 time, and because we only have one training example, we don't need to write this term over here. So this is just going to be equal to hypothesis theta of x minus y, and the hypothesis function have outputted 100 for us, and the actual value that we were supposed to get was 200, as you can see from this training example that we have. And when we calculate it, it is going to be equal to 5,000, as you can see. So what this basically tells us is we are 5,000 units away from the answer that we are supposed to get. And we use other algorithms such as gradient descent, advanced optimization algorithms to take this number and minimize it and get it equal to 0. So we use those algorithms that we're gonna learn in the future. Don't worry about it, we're gonna learn them. So we use those and we make the hypothesis function look like something like this. So now if we use the cost function to see how far away we are from the actual output or the answer that we were supposed to get, you'll see that it will be equal to 0 because we are exactly on point. We were supposed to get 200 out of the input 100. And we will get it using this hypothesis function. So you see, the cost function will not only allow us to see how far away from our answer, it will also allow us to use other algorithms to use that to optimize our hypothesis function, and as a result, the value of the cost function will be lowered. Now you might ask how we do it and why is it so important? Well, the answer lies in a really interesting fact. It lies on the graph that the cost function will make against the theta value we've chosen for our hypothesis function. Let me show it to you. So if we have this graph and this y-axis shows the j or the cost function of theta, and this x-axis shows the theta value. Now what do you think it's gonna look like? If you have guessed the quadratic equation, you are completely right. It will look something like this. I've drawn it a little bit like off, but it is supposed to be a quadratic equation. And the reason for that is kind of common sense. So let's say we are supposed to get this exact function to get the minimum value for our cost function. Now as you can see, it doesn't always touch 0. And the reason for that is we usually have a bunch of values in our data set like this, and this one, that are not supposed to be where they are, but they are. I hope that kind of made sense. We basically try to ignore these values because we know they're a little bit off. We try to have a function that fits most of the data set. It's not always like all of the data set. It's usually most of it. That's why it doesn't always go to 0. So if we had every single value in this line, which in real world examples is kind of impossible, this cost function here would have touched the bottom here. Now the reason this is like a quadratic function is because if we have this function, this goes on, this is a linear function, and this function, the distance or how far away we are from the point is similar, but this has a negative value and that one has a positive value. But the negative and the positive doesn't matter. Why? Because in our cost function, we are multiplying by itself. So it eliminates any effect of any negative number, because negative number times a negative number is going to be a positive number. So that's why we have a quadratic equation. And as I've told you, we start from like a really random hypothesis, something like this, and we use the cost function to see how far away from the actual answers that we were supposed to get. We use other algorithms such as gradient descent to optimize this value to get a better cost function, and we keep doing this until we get one of the best hypothesis functions that we can get, and the value of the cost function for that good, like the best hypothesis function, is gonna be here. As you can see, this point is supposed to be the returning point of the quadratic equation, and mathematically speaking, this is the lowest point of this quadratic equation, which means we have the lowest cost function value, which means the hypothesis function that we have chosen fits most of the data really good. So That's the general idea behind the cost function. To recap it all, we have the cost function to see how far away we are from the actual answers that we were supposed to get, and we use other algorithms to find a really good mathematical function that fits most of the data, and we can predict some new values that we've never been given the outputs for them. So we will have a function, a mathematical function, which is linear in linear regression problems, that will fit the data set that we have, so that next time that we choose a point which we don't have the answer for it, it will correspond and tell us what the answer for that input is going to be. We use the cost function to see how far away we are, and we use other algorithms that we will be learning in the other videos to adjust this hypothesis function to fit the data. So I hope that made sense. If you haven't understand it, I suggest you watch the video a couple of times again to really grasp the meaning, because cost function is something really important in terms of the role it plays in machine learning and in neural networks. So stay tuned for the other episodes that are coming up soon, and we will learn machine learning in a very simple way. Have a nice day.